All right, great. Thanks everyone for having me. Today I'd like to talk to you about one-bit matrix or vector or tensor approximations. And you can get in touch with me here. This is joint work with Sarah EK, who's the author of the famous Fair Crate. Just to touch on the software and ecosystem, I want to first qualify this by saying this is a hobby project. This is written sort of on the occasional weekend by two, people with full-time jobs, and the work here is kind of exciting. It's cool that we got some nice results out of this, but it's all on a weekend by weekend timetable. So the main output that we have here is two binaries that are able to quantize safe tensor files. So if you download a machine learning model off the internet, you can potentially be able to compress that model by a pretty large factor and still get more or less identical results. I'm also working on an image compression prototype named after my cat Angus, who's currently napping and looking very cute. And we're also working on a low-level API crate to expose some of the operations that are able to do this quantization. And there's also a research paper. My training is in pure mathematics, but I'm very much a prototyper and code junkie. And I love writing about these things. I have no idea what journal this is going to go to. I'm excited to find out who takes it. As far as the crates go, Sarah has written a lot of really cool crates that are helpful for scientific computing and debugging or benchmarking, plotting, etc. And there's a lot of cool ecosystem crates here that you maybe are familiar with. Yeah, just wanted to shout those out. How did this project start? You have no idea what this project even is yet, but I'm going to tell you how it started. So I was gloom scrolling on LinkedIn, applying for jobs, and I saw this headline for a paper on one-bit large language models, but it's actually 1.58-bit language models. So what the researchers there did was they took these very big models, occupying a lot of space, a lot of memory. And what they did was they took the floating points that are 16 bits wide, and they did some optimization problem and rounded some of them according to some problem that they wanted to solve to the quantized region -1, 0, and 1. And the benefit here is that, well, when you do forward propagation, instead of taking dot products of floating point vectors, you're only taking signed sums of floating point vectors. Not mentioned here are these zeroed out entries, so you also have to throw away some of those numbers. But you can imagine that that these might also be, if you can get the same performance, then this might actually be faster or cost less power, etc. So that's a good motivation. And this reminded me of this kind of central tool in extremal combinatorics called the regularity lemma. This is my academic grandfather, Andre Szemerédi, whose famous lemma got him the Abel Prize in 2012. What it essentially says is that if you have graphs, then you could break up their vertex sets into not a lot of blocks, such that the behavior between the blocks is kind of random. And essentially what you're doing is you're creating a grid over the vertex set of the graph. That would be the row space and the column space, and sort of averaging along those blocks in such a way that the behavior in whatever I mean by that is close enough to the original graphs. And so basically you're turning Boolean values into probabilities. But with some imagination, you can imagine that processes like this work over arbitrary matrices as well. This is a snippet from my favorite textbook, Large Networks and Graph Limits. I basically had this thing open on my desk all the time during grad school. So a few prototypes later, opening and closing this book a lot, I took the ideas in it more or less directly at face value and tried to approximate some real-world matrices using it. And I got this curve here on the top. I threw in a fudge factor, and I got this curve here on the next line. And I said, OK, this is not converging super well. And so I just decided to flip the graph theorist convention of using zeros and ones and chose to use -1s and 1s instead. So this is a swap from the unsigned cut norm to the signed cut norm. And it turns out it performs really great. You can notice that it's not even comparable. Here you get single digits errors versus maybe 50% error. And the algorithm is really straightforward. by accident, this actually sort of beats the algorithm in the Frieze and Kannan paper that defined all of these terms and techniques. This is the paper that originated the combinatorial limit theory, and it's completely missed from the randomized linear algebra community, probably because algorithms like this don't perform super well. They have like magic numbers all over them. They're more for like proving theorems and maybe not as practical. Throwing a lot of things at you on this slide, but basically I just wanted to sort of shotgun all of the different norms that are at play here. So again, these researchers are taking 16-bit floating point numbers and quantizing them down to -1s, 0s, and 1s. That's not what we're doing. We all know the Frobenius norm. It's kind of like the L2 norm, but for a matrix if you flattened it. There's also the operator norm, the first singular value. You could think about the first singular value as like a way to bootstrap a low rank approximation. So if you follow that over here, singular value decomposition, truncating the singular value decomposition at a certain rank, gets you a pretty good approximation of a matrix, but it's expensive. It's expensive because per row entry, or per row dimension, every column dimension, as well as per one extra singular value term, you have like m plus n plus 1 floating point numbers. So multiplied by the number of bits in your quantized floating point type, and then the number of rank, this number can be quite big. So Frieze and Kannan's algorithm on paper optimizes over that by, instead of using floating points in the row space and column space, they just use bits, 0s and 1s. But as I showed on the previous slide, like the convergent rate, the way that the error drops down is not as fast. But if you just use -1s and 1s and use my extremely naive like first shot algorithm, it works extremely well. You get the same like memory cost, but a much faster rate of convergence in approximating. That's bootstrapping. Frieze Kannan, we're bootstrapping like the cut norm, and the signed cut norm is defined similarly, maybe as this also known infinity to 1 operator norm. So all of these norms are like connected. It's just this one seems to perform pretty darn well. Applications. So I made some claim about compressing machine learning models. I took just whatever open machine learning model I could download and some benchmarks that I have no control over that I could just run. And I took this Mistral model, which had an open license, and compressed it by a factor of 50%, like 50% going from 13.5 gigabytes to like a little under 7 gigabytes in size, and compressed it down to that size and expanded it. And it got basically identical performance. The duck quacked like it should before. And if you look at the matrices one by one, they seem to have a lot of correlations that could be exploited. At 50% compression from the machine learning model size, the errors are all in the single digits, which is kind of shocking for, I found that shocking. There are a couple of strange matrices that behave a little bad, but that's a whole like other question to explore why. And some final optimizations I want to chat about. So the benefit of using signed sums as opposed to dot products, again, you don't have to multiply as many floating point numbers, so less error. And flipping signs is very easy. You just do a SIMD mask. This is Sarah's magic. So basically, I handed Sarah a very unoptimized prototype and got her interested in it, and she made it so very fast. Did some really cool stuff with fixed point quantizations, sparse updates. I had just suggested one idea, and it turned out it made the algorithm significantly faster. Deferred rank update. It was amazing watching her optimize this code, and least squares. Funny enough, this idea actually didn't have any impact, and I have like theoretical reasons why I think the sort of least squared correction that goes on actually didn't do anything. On the left here, I have like some run times. These are a bit in flux, so there's another implementation we're fiddling with. But again, weekend side projects, have some patience. And as far as this plot here, the funny thing here, I claimed vector approximations. So if you reshape a n squared dimensional vector as an n by n array, and you just pretend that it's an array when it's not, and you compare that to pointwise downcasting of like high precision floating points down to BF16 or F16, it turns out it works well there too. You get the same kind of approximate error, relative error, despite this having nothing to do, this being like a standard normal generated vector of floats. And finally, I promised cat pictures. So here's a variant of this algorithm tailored for tensors. So rather than running over a row space and a column space, I have a row space, a column space, and a color space. And this is a 100-fold compression of my cat. So 3,000 wide, 4,000 tall, and 3 color dimension deep. So this was like a 100-fold compression, and you can still very clearly see my cat here. I'm using the yeet keyword as opposed to return, just for fun. And this is all very like mathematical code. If you implemented this directly, your code would take like a year to run. But just with some clever optimizations, you can get this to be much faster. I think I went way faster than I realized, but thank you to everyone involved in this. Sarah, again, for all of these really cool crates. Bernard, one of my old professors, for loading me a computing cluster during the early phase when the code wasn't fast. Now the code runs like, overnight, but there I had a cluster and was biting my nails waiting for the results to finish. Sarah for optimizing the backend. It's really amazing how fast that got. Josh Cooper, old mentor of mine, for useful discussion, the organizers, attendees, and these other lovely crates in the ecosystem.
That's great. Thanks a lot for your talk. That was really fascinating. And just before we come to question, a small remark. A couple of weeks ago, we showed Sarah some code from us, and this was before lunch. Just after lunch, we got a pull request from her making our code 7 times faster. I was equally eternally grateful and very embarrassed about our own coding abilities. So it's amazing.
No. But that's how
Yes.
Well, Sarah's so good at it, and
Yes.
that was sort of my intention, was to say, Sarah, I want to start writing this paper, but like I really think you're going to enjoy this this optimization problem. And oh my gosh, it was so amazing watching her work live, and the feedback loop she had with making this code fast was really cool.
Yeah. So everyone
makes me want to learn SIMD. I think SIMD's next on my list, and I think I know who I'm going to bug about that.
Great, thanks. But other questions to your talk from the chat? So I'm really interested, actually, because you're bringing things down to a bit information. I mean, it's an underlying, almost philosophical question. Why can large language models compress so well? I mean, you showed the cat picture, but that doesn't seem the whole picture, because language is more complicated.
Well, so a lot of questions here, but if you have a set of vectors that span your space, you can project, any vector onto that and get coefficients and reconstruct the original vector, right? So it's more about picking the right basis. Floating like F32 or BF16, these are all like sort of human decisions about what real numbers should be approximated with in computers. My opinion on the matter is that like the floating, as much emphasis you can pull away from the floating point numbers, the better. So what I like about the sign vectors is that all it is a direction. It's directions, and then one floating point number per rank 1 update. And I said this thing about, as long as your vectors span your space, you're good. You can project and then reconstruct perfectly. It's a frame. So the idea here is that it's a frame as opposed to a basis.
Okay.
So you can perfectly reconstruct your whole matrix. It would take m times n rank 1 updates, but you really only need like approximately m or n of them to really get an accurate reconstruction. But yeah, I don't like all these like 4-bit quantizations and so on. I figure like you should always like you should diagonalize with -1s and 1s and have your diagonal matrix just be a couple floats. Oh, another thing I did mention is that these essentially, there's too much to say, but if you think about it the right way, this could turn machine learning models into like million parameter as opposed to billion, because you only need the diagonal of floats for each matrix. So it's like a square root in complexity there.
Yeah, don't tell NVIDIA they will take out the last remaining FP64 registers and do everything 1-bit registers. So, thanks. That was really fascinating. Any other questions or from the chat? So there's a question from Igor. Where's the crate where this is implemented? So maybe you can put some pointers into the chat.
Oh yeah. Sorry, they're all still like private right now. We're still working on like making them look pretty, but please bug me about them later. Maybe I'll work more on this over the weekend, but we'll see.